Thank you for coming. I know you had to make a decision, St. Patrick's Day or distributed systems performance troubleshooting like you've been doing it for 20 years. It's a little tough. Kill brain cells or form new neural pathways. Thank you for choosing the latter. I'm very excited to be here.
Sometimes doing both can kill brain cells.
Sometimes. Did you bring whiskey?
No.
Okay. So let me just tell you a little bit about me. I'm not just a random drifter that came in here. My career is about 20 years long. I've been doing software development, operations, just kind of on every side of building things for a long time. I got started when I was a little kid, so I've been programming for 30 years. It's been a lot of fun. It's something I actually love a lot, and it's been pretty much my passion for my whole life. I am a committer on the Apache Cassandra project, which is a petabyte scale distributed database that I was on the database teams at Apple and Netflix. I was responsible for doing a lot of the performance tuning for Cassandra for the Netflix fleet and building a lot of the software that we use to evaluate the last major release of Cassandra to make sure that it was free of defects, which has been a pretty fun experience. And I'm also lots of other stuff. I won't go into the whole resume. Just know that it's been a while. When you hop around every few years, the resume gets pretty long. But now I'm on my own. Now I help people. I do consulting. A lot of it is with Apache Cassandra, but distributed systems in general are kind of my passion. So that's basically what I'm doing. So what are we here for? To answer the question, what do we do when we have a production issue? So it's actually pretty simple. We just blame the database, and thank you for coming to my talk. But in reality, no, that's not what we're going to do. I mean, it's fun to do that, and at really small scale, it works just fine, because a lot of the times, when you have a system that's a user talking to a web server that's talking to a database, it's frequently the database. And so if you just point your finger at the database, you have a pretty good chance of being right. However, that's not what we're going to be looking at today, right? What we're looking at today is going to be a little bit more complicated. Usually, so in this type of system, you can get away with having a very, very simple dashboard that essentially tells you everything that you need to know. So if you have effectively CPU usage for your web servers and CPU usage, I/O usage, queries per second, and latency for your database, you're kind of okay for the most part. You know when things go wrong, and you really know what to point to. But when your systems start to get a lot more complicated, when we start talking about hundreds or thousands of services, each talking to their own data stores, and you're not dealing with a consistent data store, each one of these services might have its own. So for example, on the Netflix side of things, we had tons of services, all of which had their own Cassandra clusters, Mongo clusters, Postgres, MySQL, Memcache, CockroachDB, Zookeeper, and a few other things. It can be pretty tough, right? A lot of the times when we say, like, how do we figure out what's broken? The question is, well, what got deployed last? We can't even answer that question anymore, because in the world of continuous delivery, you might have 100 things that went out over the course of a day, and it might take a little while for you to actually feel the effects of a deployment. So if you had 10 deployments that just went out and you have them ongoing, it can be kind of a huge ask to ask everybody to slow down, roll everything back, and hope that it fixed the problem, because sometimes it's not even the code. So the problem with taking a system like that and saying, what was the last thing it rolled out, or blaming the database, or just trying to pick things out of the blue, is that we're essentially guessing. We're looking at this huge swath of possibilities, and we're going, is it this? Is it this? What about this over here? But when you have thousands of possibilities, and you start multiplying them together, because usually the worst performance problems and the worst outages that we have are the result of 2 or more things coming together, you end up with millions of combinations of things that could be wrong. And guessing is the worst possible option you can choose, because recovering from an outage will take you years. That is not acceptable. So hopefully, I've convinced you that guessing is not an effective means of running a production system at massive scale. What we need instead is we need a methodology, and we need great tools. So we're going to start with the OODA loop. This is something that I picked up when I was working at the Last Pickle. It's kind of a formalization of a problem-solving process. And I really like it. So the OODA loop was invented by this grouch right here, John Boyd. John Boyd was a colonel for the United States Air Force. And you might be thinking, how can we possibly apply something for the Air Force that's used to train fighter pilots over to solving production problems? Well, the reality is that problem solving in general is a pretty predictable process, and you can use the same process for military strategy as you can for solving issues in production. The OODA loop stands for observe, orient, decide, and act. So we're in the observability track. I'm going to be spending a lot of time talking about the observe part about this. The observe part basically means we look at the system before we make any decisions, before we have any assumptions, we take in a bunch of data. I don't know how many of you have ever worked in a system where something goes wrong and someone immediately starts fiddling with things, changing configurations. Yes, yes, absolutely. It is highly problematic, and people will immediately go, is it this? Well, let's try changing this, without any evidence whatsoever to support the decision that they're making. So this is a huge violation of the OODA loop. In the OODA loop, first we take in our observations, and then we move on to the orient phase, where we build a mental model in our head that supports the observations that we've made. We then make a decision about what we're going to do, and then we act on that decision. So by breaking this up into discrete steps, it allows us and prevents us really from jumping ahead in the process too much. And now, I've talked about this being a loop. The reason why it's a loop is because we might actually decide that we need more information. We might look at the problem, we might say we don't have enough information, we actually need to go digging a little bit more. So basically, we keep going through the loop until we've solved the problem. So now we're going to focus a little bit on observe with this cool pirate guy. When we start looking at a complex system, and we have at the top our application, and then we move down into services, and then we move down into individual servers, and then those servers have hardware resources, and of course those are running on a cloud provider. There's all sorts of layers to the problem that we could see an issue stem from. It gets really interesting because it's not just the servers that we control, but it's things that are out of our control sometimes that go wrong, or it's sometimes things that have nothing to do with the application that we've built. For example, if someone were to say, delete all of the security groups in an AWS account, you would have services that are unable to talk to each other, but you couldn't look at things and go, well, my CPU is pegged, and so things are going wrong because we're low on hardware resources. It's actually something that happened externally. So what we need is a system that allows us to view requests as they go through the entirety of the services and keep track of everything that happens along the way. So the best way to do this is with something called distributed tracing. Distributed tracing is one of the most powerful observability tools that you can put in your stack. It does require everybody be on the same page. It requires coordination amongst potentially hundreds of teams, but the problems that distributed tracing can solve are absolutely amazing, and it can give us insights into our applications that would be practically impossible to get otherwise. So this is kind of a really rough view as to what distributed tracing would look like. As we have requests that come through between our services, we're able to take the time between those requests as they bounce between the services and keep track of that time, okay? So for a given request, it's actually in the world of tracing, it's called a trace. We have what are called spans. And spans are essentially subdivisions out of the entire trace. Now this idea for distributed tracing came out of a paper published in 2016 from Google about a system that they have internally called Dapper. And if you ever looked at a web developer console with the network tab, that's essentially what we're after here. The difference is that the network tab tells you everything that happened in your browser, but distributed tracing tells you everything that happened in a request through a very complex application, touching hundreds of services, connecting through TCP and other means. So you can see here, this is a visualization using a tool called Jaeger. When we take our distributed tracing, our traces, and we visualize them over time. So we can see here that there are some things that occur in parallel, some things that occur sequentially, And we can even do more complex things than just trace service to service. We can even trace individual function calls within our application. So we get the ability to instrument our application as granularly as we want, and we can get incredible insights out of this. And the really cool thing is that the trace results can be aggregated together so we can get a more complete picture as to what's actually happening in our application. So this is one of the most powerful things I've ever seen from looking at a system at a high level. And this is really when you're dealing with a massive outage at a system like a Netflix, this is one of the fastest ways to get to the root of a problem. Because it's literally impossible to talk to 1,000 teams, send an email out, and say who's responsible for the outage right now. Because the coordination is just too much. There could be multiple things going wrong. There can be upstream dependencies that are breaking things downstream. There could be downstream things breaking things upstream. There's all sorts of ways in which we can fail. We can have underlying hardware failures, like EBS failing, for example, in AWS, and an entire availability zone would affect multiple services. It's not practical to have to go to multiple teams and try and coordinate that, but it is very practical to look at something and see that multiple services have been affected at the same time. That is a huge amount of insightful information, and by getting this here at the high level, we have a really, really good starting point. So at Netflix, At Netflix, we relied on Zipkin, and we stored all of our trace data in Cassandra. This was a really cool system. However, if I was building something from scratch at this point and starting over, I would look to the OpenTelemetry project. The OpenTelemetry project is pretty cool because it combines not just tracing, but other signals, such as logging and metrics, and something called baggage, which I'm not going to get into today, but it's worth looking at, into one kind of cohesive view into the way that we can observe our systems. So OpenTelemetry is pretty remarkable. In addition to tracing, it offers structured contextual logging. So one of the really interesting things that I've always thought about logging is that there's really not a lot of useful information there for reconstructing problems unless you add a little bit more data to it. And it's really hard to get a lot of data when this is all that you have in your log. Text-based logging has practical limitations. Everything has to be parsed. You have to make sure that the logging output, granted the logging libraries will give you good output, but text-based logging kind of lacks the structure that we want in order to get powerful logs and logs that we can actually search on with additional metadata. Structured logging combined with traces allows you to do things like attach a log message to a trace or add additional metadata into your logs, such as customer ID, account ID, item ID, request ID. So you can actually not only follow what happened through the tracing system and see all the times that are associated with it, but you can see the log messages that are associated with those traces, specifically with the spans that the log message originated from. So it's really nice because you can go back and get a complete picture as to what was happening over the course of a request, because everything for that request is associated with the same trace ID. The trace ID is actually propagated from service to service, and it allows us to stitch everything together. So now we have a single trace ID which has all of the spans and all of the log messages for a given request. Now there's a lot of data that can be sent over to the logger and to the tracing system, so it's really not practical to do this if you have, let's say, billions of requests a day. So typically what we end up doing is only tracing a statistically relevant but small number of requests. Google found that you can, I think they said that they can trace 0.1%, or it may have even been 1/100 of a percent, and still get relevant tracing data when you view the system in aggregate. It's essentially using sampling theory in order to get a meaningful data set that represents the entire data set. So I am going really fast through these slides. Does anybody have any questions on anything I've said so far? None? Yes.
With the log sampling, like, is that a feature of like
So you can, yeah, you can configure your logging to only send a sampling of your logging messages to OpenTelemetry, and a given request, when the first request comes in, like at the origin, that's going to be the thing that determines whether or not you're tracing. So the tracing metadata is passed along, and it's also automatic. There's code to automatically instrument libraries so that you don't actually have to pass a request ID through all of your requests. It's actually passed, it's encoded for you automatically. So essentially what you do is you pass a sample of that, and anything where you have the trace ID as part of the request, that information gets sent over to the collector, and all of it gets aggregated together as a single blob, essentially, that gets stored in your data store. So that would include the logs and everything with it.
Is the trace ID in the like HTTP headers or in the like JSON messages or protocol upload messages?
I believe it's in the TCP header. I think it's in the, I forget exactly where it's encoded. I'd have to double check on that. Someone else might know that off the top of their head. All right, I'll continue. So now that we've looked at distributed tracing, we can narrow down the problem even further, because it's not enough to be able to pinpoint a specific service to point the finger at it, because we haven't actually solved the problem. A lot of the problems that I've dealt with in production have been the result of performance issues. They've either been because more traffic has come in, more data has come in, servers have failed, hardware has failed, or some other weird thing has happened along the way. Query patterns change, the application changes, data is migrated. There's a million reasons why things can break. So we know the service now. Let's pretend that we have an idea that there's one service that's exhibiting a performance problem. Question is, what do we do with that service, right? We have to narrow it down. We have to narrow down the problem even further. And of course, there's useful dashboards. A lot of databases and other systems come with very useful dashboards out of the box, because there's multiple different types of problems that can happen with something like a database. And I'm really going to talk a lot about databases because that's what I deal with all the time, and that's kind of what I'm thinking about. And databases are particularly interesting because they tax every single resource on a computer. Databases are intense when it comes to CPU, when it comes to I/O, when it comes to network. They fail in bizarre ways. There's concurrency issues. There's all sorts of strange things that can happen with databases. So when you have multiple users of a database and they're all sitting in different queries, you can end up in a situation where it's difficult to diagnose if a particular query is causing a problem, because maybe it isn't most of the time, and maybe only when it's run at the same time as another table do you actually, or another query, do you actually see the problem. Maybe three full table scans running on a table of 100,000 rows isn't a big deal, but when there's 100 at once, it actually causes a major problem, and then we have an outage. Especially when you're dealing with a distributed system like CockroachDB here, which can have some pretty bizarre performance problems if you're not careful. So we look at this and we say to ourselves, okay, is it a query? Is it an individual query? Is it not? Maybe we discover that it is, but we're still not done with the job. It's not enough to point to a particular query and say that this query is causing a problem. It really helps to understand why a particular query is causing a problem, or why a database node is exhibiting odd behavior or a performance problem. So we're going to keep narrowing the problem down. And this is where even more dashboards are really, really useful. So we have a few common mistakes when building dashboards, and this is something I've seen at every single company I've ever worked at. So if you have some of these going on in your dashboards, it's okay, you've got some good company. One of the worst things that you can do on a dashboard is to average percentiles. If you say that my average of the P99 latency is X, and you just plot that one line, you are throwing away, you're not only throwing away a ton of useful information, but you're showing people a lie. And the reason for that is because you can't just aggregate statistics like that. If you have one request and it takes a full second, and you have 1,000,000 requests and it takes 1 millisecond, 1 second over here, 1 millisecond over here, you are not getting 500 milliseconds average P99 latency. You're just not. And so your numbers get way thrown off. And the same thing can happen when it skews the other direction. So because of basic statistics, you should not be averaging P99 or really any average or any percentile metric like this. You have to take into account all the requests, and then you can show a latency number. And the other mistake that people do all the time, and I've had to make a strong case at many places to stop doing this, is to, when you show feel-good metrics. So if you're plotting, anyone here plotting P75 or average latency? Oh, come on, someone's doing it. No hands. Okay, if you're plotting average latency, you are not getting a good idea of what your customers are actually experiencing. When you do, let's say your application does 100 requests to the database, and you say what your average latency is, and you don't take into account the high end, the maximum latency, or the P99 latency, it doesn't actually tell you that that customer is experiencing your average latency. In fact, if you go below like P75, all it takes is about 3 requests to guarantee that your customer is going to experience something outside of that latency number that you plotted on your feel-good dashboard. So the worst thing in the world is to have a dashboard on the wall that says everything is awesome when everything is not awesome, because you're essentially turning a blind eye to a potential future problem. So you really want to plot P99 and up and your maximum latency on a graph, and in my opinion, you can just throw everything else away because you're not getting anything useful out of those numbers. There is an exception to this. I was actually called out at a previous conference because you can use your average latency and queue time in queuing theory in order to calculate how many requests you can compute per hour. That is the only exception that I know of where average latency is actually really useful for you. But aside from that, don't use it. The other thing that's really helpful with dashboards, aside from making sure that you plot the right thing, is to not overwhelm your eyes and your brain. I've worked on systems where we've had database clusters with Apache Cassandra where we've had hundreds of nodes. And when you start plotting hundreds of things in one graph, it becomes a little confusing and kind of hurts my brain a little bit, at least. I don't know if you ever looked at a graph or a page of like an entire dashboard where you have literally 100 things on each graph and you're trying to scroll through really quickly to figure out what's going on, and each graph is just like spider web of just information. It's just chaos. You can't possibly get useful information out of that. So the best thing that you can do in this case is to actually just plot your outliers. So this is a graph that I developed at Netflix, where instead of plotting everything on the graph, we would only plot the worst performing nodes, and then we would basically plot the median just to get an idea of what was going on with the rest of the cluster, and then we'd plot the best performing node. And so when you look at the difference between the worst performing node and the best performing node, it gives you a really good idea of what your range is, and then that middle line kind of gives you an idea of where everything is performing, but it does so without the visual clutter. Let's also remember that a lot of the graphing tools that we use won't do a great job of plotting that much dense information into graphs. The rendering gets really slow, and it becomes really hard to actually dig in. And if you don't like using your tools, then you're probably not going to use them. So you definitely don't want a situation where you dread opening up your graphing tool because you end up with 20 seconds of waiting and then a graph that like destroys your entire machine. So by plotting the outliers, it gives you the opportunity to, in a clustered environment, see the things that are performing poorly. This is, as I mentioned, this is what I implemented at Netflix, and this is still in use there to this day, and it is what is used to solve all of the database performance problems across the 35,000 Cassandra nodes that they're running in production. So it works really well. So now, what am I doing? Oh man, so much time. So now we've managed to use our traces, and we've managed to say, hey, the problem is originating at the database. The database has slow queries. It is Cassandra. I knew it was the database. You're wrong, John. Our job is over. But our job actually isn't over. We now have to go in and figure out what is causing the problem. And so when it comes to performance problems in databases, it's a little bit tricky because scaling databases can be time-consuming. It can take a long time to scale databases, and it can be expensive. If you have 30,000, 35,000, or if you're at Apple scale, 200,000 nodes, being inefficient and just scaling things like crazy is a really good way to waste tens or hundreds of millions of dollars. So we're not going to do that here. What we're going to do is at least try to get an understanding of what is the root cause of the performance problem. And most performance problems that I end up seeing are the result of resource starvation. We just don't have enough resources. However, the root cause of that is actually that something typically is misconfigured, or we have non-optimal data model, or some other underlying cause that is causing excessive resource usage. So the goal isn't to say, how can I continue using this system in the way that I'm using it and change nothing other than the amount of hardware I'm throwing at it. The goal is to figure out how can we use the hardware that we have more optimally and we can save money. The reason why I say that is because in my career, I've done some work on Cassandra clusters where I've gotten an improvement in both throughput and latency by an order of magnitude. So if we're talking about firing up 3 nodes in a cluster or 30 nodes or 100 versus 300, the cost difference is pretty insane. And again, if you're talking about $100 million versus $300 million, it becomes a no-brainer to spend a little bit of time doing an investigation to figure out how we can better utilize our resources. So to do that, I'm going to introduce a new process called the use method. So I did not invent this. This is taken from Brendan Gregg's website. He's a Linux performance expert, one of the most authoritative people in the world. And this QR code goes to his page on the use method. You can dig into it. It's a lot of fun. I literally use this all the time. The use method stands for, the U stands for utilization. So the thing that we want to understand first is what is the average time that the resource was busy servicing work. For the case of a CPU, if you open up top or MPstat or a tool similar to that, you're going to see that you have whatever number of CPUs and how busy they are. So 65% CPU, or in this example, 90% CPU. Really, really helpful to understand that utilization because if you see that your CPU is really high, then you can make a reasonable assumption that we're asking it to do quite a bit of work. The next part is saturation. So this is the degree to which the resource has extra work where it can't service. So this is really easily visible when you look at I/O. So especially with older drives, or if you've worked in a cloud environment and you haven't provisioned your drive with a lot of IOPS, or it's the older like GP2 type drives in Amazon where it just doesn't have a ton of throughput. What ends up happening is you have these big bursts of I/O, you get limited, and then they will have a queue. And so you're sitting there and your drives are queued. So it's really, really important to be able to identify when you have a queue on the underlying system. And then we have errors. So utilization, saturation, errors. Our errors tell us a lot. I once worked with a customer that was in Oracle Cloud, and they were blaming Cassandra because Cassandra was returning slow responses. Well, it turned out that the Red Hat version that they had deployed had a bug where NVMe drives did not work correctly. So most of the requests that would go to the NVMe drive were erroring out. And it was only through an investigation that we were able to determine this. So people are saying, why does Cassandra take 500 milliseconds to respond to this like tiny request? Well, it's because you actually have an issue with the kernel that you have in your deployment. That was a long time ago. I'm not trying to talk about Oracle Cloud here. But you can see how this would be an issue that would affect performance in a really weird way. You wouldn't see high CPU usage. You won't even see high I/O usage, but you do see a ton of errors. So when that happens, it's really helpful to understand the right tools to use to diagnose that problem. So I mentioned this already. There's a really great library that's been around for forever. I mean, I think at least as long as my career, IOStat. Now, IOStat is a very, very useful, I'll call it a high-level tool because it doesn't really give you granular information about what's going on in your I/O devices, but it can give you a pretty good read on things. You can get a quick understanding of what throughput and average latency of your drives looks like. There's a lot of options to IOStat. In this one, I'm using, well, I have DMC here. I usually use DMX, not just because he was a wonderful rapper, but because the output is genuinely very useful. So you can see here that if we were actually doing some I/O, we would see that we would see the throughput represented in the MB reads, MB writes, etc. For understanding CPU, there's another really useful tool in the same package called MPStat. MPStat, multiprocessor, can break out your per CPU utilization, and it'll also break it out between user and I, system, I/O weight, etc. This is very, very valuable because you want to have a good, like this can kind of help you decide what your next step is going to be. If you see, for example, like I did the other day, that I had 25% of my time was spent in sys, I was then able to follow that up and determine that I was seeing 30,000 Futex failures every second, which is a really bizarre thing to kind of just be like, why are we just waiting on a lock with 25% of our CPU time? That seems like a problem. Maybe we should investigate. Now, this brings me to my favorite topic of discussion. I have been trying to tell everybody in the world about these tools for a long time now because I think that this is, the next few slides that I'm going to show you have enabled me to work on some of the hardest problems in distributed systems at the highest level of my career. Solving problems at Netflix when we've had database outages with like subscriber database, performance issues that affected 600 node database clusters replicated into 3 DCs, like huge money on the line, and these were the things that allowed me to solve the problems that we have. So I'm a huge, huge fan. You can see from the graph here, or from the image here, there's a ton of tools. I'm not going to talk about all of them. I'm only going to talk about a handful of them, and I'm going to walk you through what happens when I notice that there are I/O issues on a machine. I deal with a lot of I/O related either questions, speculation, concerns. While I was at Netflix, one of the biggest things that one of the things that I worked on that was especially tricky was we had moved a Cassandra cluster from Cassandra 2 using Thrift, which is the old interface, to Cassandra 3 using CQL. So we had a version change, and unbeknownst to us, because I showed up 2 years into this migration. This was literally a 2-year migration because it was the billing and subscriber system, like kind of critical that we don't lose data in this thing. When I showed up, they had just shifted traffic from the old database to the new database, and all of a sudden our P99 latency goes from about 6 milliseconds to 90, and we're sitting there going, what's going on? And everybody's thinking, it must be EBS because we also changed EBS in this process. The team was ready to scrap the entire project and literally throw away like a 2-year migration and then have to like go through a whole process, revalidate. It would have taken us weeks to revalidate that when we switched from EBS to instant storage, that we had the correct data because we had to run multiple validations. This is how I figured it out, these tools. So at a high level, we have a file system. And one of the interesting questions that people, that you should ask yourself, if a database is operating slowly and we are going to blame the storage system, what kind of response times are we actually getting off our storage? So the first thing that we can do is we can use XFS dist to look at every single I/O request that goes through the file system and to generate a histogram to show us the distribution of response times. So typically, on a database system that's fairly busy, and this was just taken, I think I was working in a VM, so there wasn't really a lot going on. But if you're working in an active database system, you're gonna see a bimodal distribution. You're gonna see a whole bunch of requests that are really fast, and then you're gonna see some that are really slow. And the reason why you see that is because a certain percentage of your requests, hopefully a lot, are being served out of page cache. And then depending on how slow your underlying drive is, you're gonna see that second distribution where you have everything that actually went to disk. So the next logical question that people will ask is, well, how can we tell how much data is getting pulled out of cache and how much data is actually going to disk? Because this is pretty valuable. What is our response time on our disk even looking like? Well, to answer the first question, there's a really great tool called CacheStat. CacheStat can show you how many hits and misses and the percentage of hits that you have along the way, along with a little bit of extra information about your cache. And so as soon as you start taking a look at the numbers that are coming out of your file system, you start taking a look at the cache hit ratio. And by the way, the problem that I was looking at, we were actually seeing 99% plus cache hits. It starts to become a little bit more obvious that the block device is not the problem here. So then to prove it finally, we have to ask ourselves, okay, if we know that we are seeing this at the file system level and we're seeing 99% cache hit rate, which means we're almost never going to the block device, how often are we actually going to the block device? What does this look like? Are we seeing any additional overhead because pulling things through the file system, like we might be getting some weird numbers there. Let's just run another tool and check. Bio latency, and there's a whole bunch of other tools that start with bio, it's block IO, is an incredible tool. So this will show you the same type of data as that XFS disk tool. And by the way, if you're using ext4, ZFS, BTRFS, the same tooling exists for all of them. It just plugs into different parts of the kernel. And so you can use bio latency and it will show you your distribution of response times for all of the requests that went to your block device. So by using this, I was able to prove that it was impossible that the underlying drive could be the thing that was responsible for the slow requests. And I just want to point out one more interesting thing about this that I forgot to mention. So all this, because this is based on eBPF, this is essentially code that you're sending over to the kernel, and you're essentially saying like, hey, I want to understand what's going on at the kernel level. This is being run inside a virtual machine in the kernel, and there's very, very little overhead from it because it deliberately protects itself from being overrun by a ton of activity. So when I run this stuff in production, I see less than 1% overhead from running these utilities. So whenever I have a problem, it's one of the first things I reach for, because understanding what's happening at a resource level during a performance issue is one of the most critical aspects that we have, or one of the most critical things that we can do. So the next thing, profiling. I got into this about 5 or 6 years ago. I love profiling, and a lot of folks are familiar with profiling from like event-based profilers, where it will track everything that happened along the way. One of the problems with event-based profilers is that as soon as you start watching everything that's happening, you actually interfere with the performance of the system, because if you're instrumenting every single line of code, it's not going to be great. Like, you have way too much overhead associated with the running application. So everything slows down, things run poorly. I highly recommend taking a look at sample-based profilers. Sampling-based profilers are fantastic. They're essentially taking constant snapshots of what's going on in the system, and because we can use sampling theory, as long as we collect enough snapshots of what's happening in the system, we can aggregate them together and get a pretty complete picture as to what's going on in our running program. So, my favorite way of using my profiling data is with flame graphs. We had this, flame graphs were invented, again, by Brendan Gregg, and you can use them to display a lot of useful information. So here's a flame graph from Apache Cassandra, and I think it's Apache Cassandra. It's probably Apache Cassandra. And so what we have is the ability to visually inspect what's going on inside the running application. The height, each of those bars, represents a frame in the stack. So it's this method calls this method, calls this method, and it just grows up. The thing at the top that's in blue, those are the JVM intrinsics. So we're actually seeing there that we're doing like a byte allocation, for example, a byte buffer allocation. You can also see, if you instrument it correctly, you can also see system calls. So you can see when, and those would show up in red. This is using the async profiler, which I highly recommend for doing, if you're using Java, the async profiler is an absolutely amazing tool, and it can generate this with almost no work. So essentially what we have is the call stacks go up, and the width is the amount of time that the application, that the CPU spent in that relative thing. So at the bottom, it's wider because it says all, and then that's the entire running application. And as it goes up, you get a better and better understanding of where your time is spent at the, at the very end of things. So here we can actually see that we're spending a lot of time allocating byte arrays. And that's not great, right? We definitely don't want to spend a ton of time just allocating memory. We want to be more efficient than that. We can also do some other cool things with this. I didn't include the image, but we can generate it upside down. So we can go from the tip down, which is pretty cool, because if you have multiple code paths that call the same thing, it's really hard to see that maybe you reach a certain code path and it takes 2% every time at the tip, but when you aggregate it together, it's like 40% of the running program. It's a really, really good idea to do an icicle graph as well. And it's with async profiler, you just pass dash reverse, and it will just generate that for you. Now you can also do the same thing. You don't with trace, which is built in. I don't remember if it's a built-in thing on Linux, but it's certainly available that you can install it. So you can profile any number of ways. It's really just flat call stacks, and the flame graph. You can either use Brendan Gregg's flame graph software to visualize it, or the async profiler, which uses sample-based profiling. Can do it as well. Now, one thing I also want to mention, and this is really important, if you are going to profile Java applications, it's really important that you go for a profiler that does not suffer from safe point bias. Safe point bias is if your profiler is essentially waiting for your application to reach a safe point before it reads the stack. The reason why that's not good is because a running Java application will not reach a safe point everywhere. There are certain things like memory map file operations that it will only stop at either side of, before it begins or after it ends. It won't stop in the middle. So your call stacks will never show that you're waiting on memory map files. They'll only show that you're doing something else. So you end up hiding certain operations. It also, in certain hot loops, it won't do a safe point. So essentially, async profiler is really nice because it takes the snapshot of the stack asynchronously, and it doesn't wait for it. So it can be a little off occasionally, but the benefit is that you catch things like memory map file operations, and you can get a lot more details from it. Now you can do a lot more than just CPU profiling. You can also do allocation profiling, and you can do off CPU profiling. So off CPU is whenever you've sent something away from your user program, and then you're saying, hey, go do some I/O, or you need to lock, or some other activity. Like if you look here, I don't know if it's really visible, but at the top of this, there's a whole bunch of locks happening. This was actually the issue that I was talking about earlier, where I saw there was a whole bunch of futex calls. Still trying to figure out what's going on there. But the point is that we can essentially figure out what's going on with anything. When it comes to allocation profiling, the reason why I love allocation profiling is because when you're dealing with the JVM, GC pauses are very, very highly correlated to the amount of memory that you allocate. If you're wasteful with memory allocation, you will end up with more frequent GC pauses, and they will take longer, especially since there's a higher likelihood that the data that's being inspected for garbage collection will still be alive, and then it needs to be promoted. And whenever objects are promoted, they're copied, and copying objects takes a lot longer than just ignoring them and doing nothing. So essentially what you have is this terrible cycle where you over allocate, and you have longer GC pauses, and you have them more frequently, and then you copy more memory around, and then you can end up with, especially with either G1 or Parnu and CMS, and even ZGC and Shenandoah, you will have this problem where if you over allocate, you will eventually end up with stop the world pauses, and it will grind everything to a halt. I just evaluated ZGC with Cassandra, and because of the amount that we over allocate, it was completely unstable in a pretty light environment. Workloads that G1 GC was able to handle, ZGC completely fell apart, the entire cluster locked up, and nothing got done. Unfortunately, I don't have the graph here where it shows the heap usage where everything just became a mess. But essentially, you can end up, through over-allocation, end up in a situation where nothing works. So that's why I love heap allocation. Okay, enough of that. So what are we, what is actually our process like? Let's kind of go over this. You want to start at the highest level that you can, right? If you know that you have a service that's a problem, you can start with the service. If you get an alert and you know that that alert pertains to something that you run, you can start there. You don't need to start at the high level. You don't need all the traces. But if you're trying to understand why is Netflix down, then it really helps to have the traces, because people do not like it when they can't stream, Love is Blind, I guess. So you really need a system like this to be able to quickly figure out what's the root cause of the problem. And then just keep narrowing it down. Structured logging can help you identify specific types of issues with individuals at the request level. And then you can aggregate the stuff, and you can aggregate the things that, like a customer, if you add the additional logging, or span, the individual span, so you can see all the logs for a given trace, so you get a lot of useful information there. And then finally, like I said, my favorite thing, the ultimate problem-solving tool is eBPF, which is BCC Tools and Flame Graphs. They have provided me some of the most comprehensive understanding of running applications in production at Apple, at Netflix, at Spotify, at banks that I've worked with. Every single team I've ever worked with in the last 5 years, at some point, I've probably tried to bust this out when there was a performance problem. And I forgot to mention that I'm the guy that people call when there's a dumpster fire. So I literally am doing this all the time. It's a lot of fun for me. I really enjoy it. I really, really hope that you all got a lot out of this talk. I wasn't sure if I was going to give too much information, but it looks like we're just at the right amount to be able to take some questions. So thank you very much.
Hey, thank you. In terms of the performance tools on production, usually production's locked down. How do you kind of manage that, and especially in container environments where maybe you want to, ship things in container, ship your performance tools in containers?
Oh wow, you've opened up Pandora's box for me. Okay, so that is a really great question. So it's a combination of a people problem and obviously the technical. I won't deal with the people one because I'm not an expert on people. But as far as the container stuff goes, I would build these things into the container. I actually have recently, as of just a couple days ago, have been working with a team that decided to use Kubernetes to deploy Cassandra. And helping them fix problems has been one of the most frustrating things I've ever worked on, because containerization is built on the idea that you don't have to care about the underlying performance and you can just throw things away. That works wonderfully if it's an application server and things are running fine in the application, but when it comes to a stateful system like a database, I think it's an absolutely horrendous choice, and I would never put a database, at least not today, I would never containerize a database, and I wouldn't put it on Kubernetes for sure. I think it makes the job 100 times harder with zero benefit, other than you can reattach a new pod to a volume, which you could do before without any real issues, with just some very basic automation. So as much as I like Kubernetes for stateless stuff, and I can talk a little bit about the system I developed at Apple that fully relied on a 1,000-node Kubernetes cluster in order to test the Cassandra 4.0 release, I absolutely despise it in its current form for stateful systems. So bake in the tools into the container. They can be used. You have to be flexible with permissions. But to me, anything that makes it so that it's harder to observe the state of the system and to diagnose problems, to me is a complete, it just eliminates it as a useful tool for me. Because this is, to me, observability is one of the most important aspects of running anything in production. So hopefully my little rant is
Hey, I got more of the same, sort of. So, my problem is that, you know, I'm an old sysadmin, and I'm used to SSHing in, running, you know, the sysstat tools or whatever, figuring out what's going on. The problem is, like, these days, like, even if you're not in a container, like, they don't want SSH enabled on these machines, right?
Yeah.
That's a no-no. And so the thing I need to do is I need to, so how do you just ahead of time figure out all the eBPF stuff you need to export ahead of time? Or do you change that while you're having a problem, do some rollout of your Puppet config, or like, how do you address that? You know, I don't know ahead of time what I want to look at problem.
Yeah, that's a really good question. I try to bake in, fortunately for me, I know the tools that I use. There is, in the like Ubuntu, so I always use Ubuntu. Within Ubuntu, there's a BCC tools package. I install that on everything I work on. I would make that mandatory. That comes with all of this. All of this is there. So for me, I set up the flame graph, async profiler, that's installed. BCC tools is installed. And yeah, that's to me, that's mandatory. The idea of not SSHing in is really strange to me after, I'm guessing we probably have a kind of a similar background. I've been SSHing into stuff for 20 years. I'm not stopping. I don't care. Like, that was one of the really nice things about working in Netflix. We didn't have asinine rules like that. I could do whatever I needed to do to solve problems. I had no restrictions whatsoever because they just put trust in the people. In an environment where someone says that they don't trust you to do your job, they're inherently making it more difficult for you to do your job. And I find it to be incredibly frustrating when people put rules in place that make it hard for me to do my job like that. So I would fight that really hard. Or in the past, I may have gone a little rogue and just kind of done whatever I wanted to do anyway. Yeah.
So did you install these tools on the image, container image, or the node? So did you install these tools on the container image or the host node?
You can do it either way. I prefer to have everything on the host node because having a good understanding of the host system is really important. If you put it in the container, then you can set a handful of permissions that allow the container to get the introspection that it needs. But because you need access to like the kernel to do the instrumentation, you're essentially saying like, okay, like within the container, I can talk to the host node. Some people don't like that because it breaks kind of the illusion of what containerization is supposed to give you, this kind of like, we don't really care. But yeah, I strictly don't do it. I actually have a project that allows me to build, it builds a Cassandra universal AMI that has every single release in Cassandra from starting with version 3.0, and it bakes in all of these tools from and it compiles them and just builds them in, because to me, to do an investigation, to be effective, this has been literally the most powerful thing I've ever worked with from the standpoint of being able to understand what's happening in my system. So to me, it's crazy to kind of work with my hands tied when I know I could have this. So yeah, I would basically get it everywhere I could.
Thanks.
Oh, and by the way, you could actually see different results from like if you had C group limiting the number of IOPS in your drive, you could end up seeing like your file system could be slow in the container, but it could be totally fast outside of the container. So it's actually useful to be able to have both types of introspection where you can see what's happening at you know what I'm saying? Like it's like the more places that you can measure, the better. You don't just want to measure a database from whatever the database tells you. You want to measure a database from what the driver tells you as well, because there's going to be some differentiation in there. And being able to understand that is critical to solving performance problems.
I have a question on like, how do you balance like time that you spend on upgrading your tools, or maybe even like just fixing things that have degraded with your tooling for observability, with, you know, solving problems on a time crunch, and also like just other responsibilities one might have, since, you know, one thing that's felt like a constant frustration in my experience, and like maybe this actually isn't too common, I don't know, is that tooling, you know, thinking of like stuff like distributed tracing or like APMs and stuff, it feels like a lot of times they've just been like so fragile in my experience sometimes, like they'll just break, and then it's hard to figure out why they're broken. Or, you know, maybe on a similar theme, is there anything that's just like super reliable, like even if everything else lets you down, you can just get SSH in, get some observability? Yeah, any thoughts on that?
Yeah, so for me, like, again, it's this. Like the reason why I push this so hard is because at the end of the day, once you're on a single server, it really helps to be able to say, okay, this is exactly what's happening at the CPU. This is exactly what's happening at the block device. This is what's happening with my page cache. Yeah, like orchestrating distributed tracing can be difficult, but because it requires every single team in the organization to buy in, and it often requires coordination amongst all the teams. So getting that rolled out can be super tricky, especially if you're at a massive, like really massive scale where you've got hundreds of services. It's like, how do we get a mandate for 100 teams to all do the same thing without arguing and dealing with product people that want their stuff and whoever. I forgot the original question before I started rambling.
I think that mostly touched on it, yeah.
Okay, cool. If you can't tell, I really resent anyone telling me what to do.
Speaking of which, this is more of a human element question in an outage troubleshooting situation, but how do you deal with management that wants to be involved in the session that's, throwing out all kinds of random, throw it at the wall kinds of suggestions and kind of distracting, from going through the OODA loop in a systematic way without shutting them out completely. I mean, they need to probably report to their superiors what's going on, but you just don't want them directly involved.
Yeah, human question. So ultimately, I think the way to deal with kind of people in that sort of conflicting situation is to come from a place of empathy. So they have their own thing. You kind of have to recognize that what they're dealing with, but they're also, if they're getting in your way from actually getting your job done effectively, it really is going to come down to clear communication with them without coming off as resentful or mean or just rude. So I think in that case, in situations that I've been in, I've just said, hey, like, you know, like I will get to this, but you need to just let me do this, and I will solve this. Like, and you know, you can kind of escalate it, but there is a certain point where if they're trying to micromanage you, then maybe you just let them try and solve it on their own and let them hang themselves in the process. Like, I unfortunately, like I said, I deal a lot better with my just being me and solving technical problems, but when it comes to those kind of situations, that's actually one of the reasons why I went to Netflix, is because I never had that kind of overbearing management there. It was just get your job done and be awesome and you're fine. So yeah, I wish I had a better answer for that one. I'm definitely sensing a vibe of management is making things worse. Yeah.
As a manager, let me ask you,
Yes.
you said that almost all of the problems were resource starvation of sorts. My question is, what are the ones that aren't, or what tool you wish you had that isn't enumerated here?
Yeah, one thing I didn't talk about today is debugging situations which are either like a threading issue where you have deadlocks. Fortunately, you can rely on flame graphs to actually show you when you have lock contention. And you can also have situations, like I mentioned earlier, where someone runs a script that accidentally deletes all the security groups in an entire environment. Ugh, what do we do then, right? Those problems are a lot harder to solve. That especially is difficult with distributed tracing because now you can't send traces in. So when someone accidentally deletes everything that you have, those problems become really tricky, especially since in those scenarios, the people that need to fix the problem are also locked out of the systems that, that can fix it. Yeah, those become really hard. It still is a narrow down the problem situation for those types of things. Like, you know, it's still about make observations. Like, nobody can SSH in. Nobody can access anything. That is actually an incredibly powerful observation. So if we just take that and we say, let's orient ourselves from that simple observation of we can't access anything, then it leaves us with a handful of possibilities. It's a, you know, the data center has been hit by a tornado and is destroyed, or, you know, or you just can't reach it somehow at the networking level. And effectively at that point, like, you have a handful of possibilities that it could be, and then it's kind of just a process of elimination. Okay, is the data center exist, right? Ruling that out, that's a major catastrophe. Was it nuked? No. Awesome. Now we move on to the next thing. Like, is it a networking issue? So effectively, if you think about it as like bisecting the problem space until you eventually get down into the one remaining thing that it could be, that's kind of how I approach just general problem solving. So that's why I always say, start with the top, start with the high level, and then you continuously narrow it down. And then Occam's razor effectively gives you, like, if you get to a point where there's only like a couple things left, it's probably that. And the whole point of doing the loop is you're constantly challenging yourself, and you're challenging the assumptions that are being made, and you're gathering more data, and you're ruling things out, and you're saying, okay, like, here's my problem space, let's make it smaller. So I really truly think that the OODA loop is the ideal tool to solve any problem when we start talking about, especially when we're talking about distributed systems performance. And I've never known a team to employ another strategy like guessing to solve it. It just doesn't end up working. There's too many things otherwise. Yep. Oh, microphone.
So in the beginning, you mentioned the OODA loop and the first two parts of it. Is there anything you do in particular on the decide and action steps
Yeah.
to solve these problems?
Yeah, I mean, decide is like it's fairly short, right? We are going to do X, but one of the most important things about deciding and acting is clear communication with the other people on the team. And this is one of the other reasons why jumping in and just fiddling with stuff doesn't make any sense. Early on in my career, I actually did go in and just start restarting things, and it turned out other people were restarting things, and we weren't talking to each other, and like, I kind of made a problem worse, and it was all bad, right? You definitely need to have clear communication throughout the team. So when you start making that decision, it's what is happening and who is responsible. Those are two super important things. And when it comes to, there is one other thing in there that's actually pretty important, is what happens if the decision is wrong? Do we have a rollback plan? So the decision of what to do is, you know, it's a little bit more than what to do. It's what do we do, who's going to do it, and what happens if it goes wrong, and then act as the actual person who's responsible, taking control of the situation and acting. Now, again, decide and act could be, we need more information, and it frequently is. I go through a lot of cycles of this where it's like, okay, I see this, and I'm just sitting there and I unconsciously make the decision, I need more information, okay, let's go get it. So I'll seek out as much information as I can in order to build a mental model, which helps me understand how all of the different components of the system are interacting. And only then, once I have it, I will literally say, I am doing this because I see X, Y, Z, and for these reasons, I'm going to do, so-and-so is going to do this, usually me. So that's kind of, it helps paint a clear picture of what's going to happen. It assigns the responsibility of who's going to perform the action. And then if it doesn't work, the plan is this. One of the reasons why I like Cassandra so much is because I can actually just test stuff sometimes. Like, I'll test things in production. Sometimes they don't work, but because it's a replicated, because we have multiple replicas for every copy of a piece of data, I can very safely test configuration changes. And in fact, most changes, even ones that are schema related, without impacting the rest of the cluster. So, test in production, hey. Yeah. Anything else? I don't know if I'm going to get kicked out. Lunchtime. Oh. I mean, I can stick around and ask questions if people want to hang out. I'll happy to answer stuff. All right, last one.
Did the deletion of all the security groups make you reconsider whether everyone should be able to just SSH and prod and run whatever script they want?
I have some, okay, so I can't tell you who did it, but I can tell you that it wasn't the result of someone SSHing into production. It was the result of a drive running out of storage space. And then it happened to go down a code path that had never been hit because it thought that there were supposed to be no security groups, and it was set to auto-apply whatever changes. So think of it as like, it read the output. It read the desired state as no state, and then eliminated thousands of security groups. Fun. All right, I'll take the mic off, but I'll hang out for a little bit if anybody wants to chat. Thanks everyone for coming. Appreciate it.